So I've got a few more kind of small properties of functions that I want to talk about here. And the first one is what it means for two functions to be equal. And this is really a relatively kind of trivial definition, but in math, definitions are important, right? So we do want to kind of officially lay out what it means, just so we have this in our back pocket in case we need it. So two functions, right, and defined for the same domain, right? They're both, the domain is x here, and for the same codomain, both of them are y, are equal if and only if f of x is equal to g of x for every x in that domain. In other words, if they match for every possible value, right? Pick any x out of the domain, find the f value and the g value, they have to match up. It's exactly what you'd kind of expect for it to mean for two functions to be equal. All right, whether or not a function is well defined, this is actually a bit of a tricky bit of terminology here. If it's not well defined, it isn't a function. So our rule here is that functions need to be well defined, right? And essentially what this means is that it has to pass both of those two requirements, and we get the same output even if we rewrite an input value in a different way. So the way we write a number, for example, do we write a fraction as 1/3 or 2/6? Those two fractions both represent the same value. So even though they look different, they should get mapped to the same value in the codomain. All right, so I've got an example here for us to look at. I'm trying to define a function from the real numbers to the real numbers such that this is true. Right? This is how we're going to find the relationship. We're not using an arrow diagram anymore. We're now doing this using a formula, which it really is, I'm sure, the way that most of you are accustomed to seeing functions defined. So I want you to stop and think about this for a minute, right? See if you can figure out why this would not represent a well-defined function. Okay, so remember the first rule, first part of the definition. Every value in the domain has to have a matching value in the codomain, and that is not the case here, right? For example, 2 is a real number, but if I put 2 in here, I get 2 squared plus y squared equals 1. That's 4, right? Move it over to the other side. Y squared equals -3, and okay, yeah, that can happen, but we're going to have to fall back on imaginary numbers. There is no real number, right? There is no number here in the codomain for which that is true, right? So therefore, this is not a well-defined function. Now, as we saw in at the end of the last lecture, we were looking at examples of things that weren't functions. Sometimes we can fix this, right? Sometimes we can fix this. For example, let's say I narrow this down. Let's say I take f from -1 to 1 into the real numbers. Well, how about now? Did I fix my problem? Well, unfortunately, no, we didn't. Right? And to see why, just take that right-hand end value. Let's put 1 in there for x. Right? 1 squared plus y squared equals 1. Oh, I shouldn't have picked that one. Sorry. Don't pick that one. Let's do 0. Right? Let's let x equal 0. If we do that, we get 0 squared plus y squared equals 1. All right, so that's y squared equals 1, and now we're in trouble. Y equals plus or minus 1. My formula here that I'm using to define the relationship between the domain and the codomain, it's kicking out 2 y values for 1 x value, and that's not okay. Right? That's not okay. So let me ask you again, can we fix this? Right? Can we fix this? And I actually want you to think about that for a minute. Right? See if you can come up with a way to fix this situation, because we can. All right, so we can if we take this one step further. Now I'm going to stick with what I've got here, but I'm also going to put a restriction on the domain, right? I'm going to, excuse me, on the codomain. I'm going to restrict the codomain to just positive numbers. In fact, that works. Well, we could lighten this up a little bit. We could even just say R plus, right? Positive real numbers. Now that fixed the problem. Now this negative one here is no longer an option, and we would only be getting one value out. So sometimes we can fix it, right? But this is something you just kind of need to have in the back of your mind. It's not going to come up very often that you're going to be given things where you turn around and say, okay, wait a minute, that's not really a function. But if you're doing any kind of research, maybe you're trying to come up with your own models for things down the road, right? This is something you need to be aware of. All right, so our last item in this lecture is this idea of function acting on sets. So everything we've done so far, everything you're used to for working with functions, involves functions acting on elements of the domain. For example, A is an element of the domain here, and we would say that f of A is equal to P. Right, but we can expand this a little bit. Right? Instead of letting the function just act on individual elements out of the domain, we can actually let it act on subsets of the domain. For example, let's say we let A be the set A comma B. Right, then I can talk about what is f of A. Well, it's not an individual value anymore, right? The image of a subset is, generally speaking, going to be a set. And here, let's see, A goes to P and B goes to R. So here I would say f of A is equal to the set P comma R. So this is just kind of expanding our notion of the things that we can use as input values for a function, right? They don't have to be individual elements. They can actually be sets as well. All right, so those are kind of our basic concepts, right, that we're going to be relying on here. In the next lecture, we're going to talk about what it means for a function to be one-to-one. And that's an idea you've probably heard about before, and in your algebra classes, it's an important concept when you're talking about whether or not a function has an inverse. So we're going to revisit that here in the next lecture.